Okay, the last thing we talk about polar conics is intersections, or the systems of polar conics. Okay, that's the last thing we're going to do on conics for this week and for a little while. We're going to switch over and do a little different topic, and then we'll come back to some things at the end of the year once we finish that other topic. So okay, so let's talk about this one. So we have the first conic. Conic 1 has an eccentricity of 5/4, directrix at y equals 2, and the focus is at 0, 0, or one of the focuses. Say one focus. Okay, and this is the directrix for that focus. Okay, the second conic has an eccentricity of 3/5. The directrix for that is x equals negative 5, and this is the directrix for the focus at the origin. Okay, so our question here is find the intersections. And we're going to find those intersections in polar form. Okay, so if we look at conic 1 here, right, for ourselves, okay, remember our equation, ED, and then 1, and then we have to figure out what exactly is going on here. For this conic, right, we have y equals 2, right, so it's going to be opening down. Our conic is going that direction. So if it's an ellipse, it's opening down. If it's a parabola, actually it's not a parabola because it's 5/4. It's going to be a hyperbola, so the other branch is going to be up here. Okay, for ourselves. All right, so if we look back and we find our equation there, that equation is going to be, let me just make sure I got the right one. Okay, it's going to be the 1 plus e to the sine theta for ourselves. Right? Okay, sine, because if we're thinking about that distance, that's a vertical distance there, right? So that's where the sine, and for sine when it's above, it's plus. Okay, so we have the distance from the focus to the directrix. That's the d there. That's 2, right? So 2 times 5/4 gives us 5/2 for that in the numerator, and then the denominator 5/4 sine theta. Okay. Okay, and if we multiply by 4 for ourselves, we'll get the 10 over 4 plus 5 sine theta, right, for ourselves. Okay, right, and okay, so we have that equation. Right, I'm gonna make the example I'm going off of says make a sketch to support your answers, and having that definitely does help because you can kind of see where your answers are. But let me hold off on that for a second. Right. So let's do the second equation here. Right. So if we look at the second one, we have let's see. We look at this. Think about the second one, and I'll put it on the same graph here. 1, 2, 3, 4, 5. Okay, so it's going to be an ellipse, right? And it's going this way. So that was our r equals we have ED1 minus E cosine theta. Okay, cosine because this distance is our horizontal distance, and that uses cosine, right? And for that, for because it's to the left, right, it's going to be minus. Okay, so we have that on our equation then is when we put it in, right, e, the distance being -5, so it's going to be -3 on top, right, 1 minus 3/5 cosine of theta, right, we're going to multiply it by 5, so we'll get -15, 5 minus 3 cosines thetas as our equation for that second one there. Sorry, our d was positive. Our x was -5, our d was 5, so that becomes positive. So those are just positives there. So I'm going to go back and fix that. Sorry about that. Okay, so we have our two equations. We just have to figure out where those two equations are going to be equal to each other. Right, so we'll set 15 over 5 minus 3 cosine theta equal to 10. Whoops, I was going to put the same equation there. 10, 4 plus 5 sine theta. Okay. So there are going to be some systems that are easier to do if we just have the polar form, right? And maybe this is going to be one of them, right? Usually if it asks you to do polar form, it's going to be easier that way. Okay, so because of that, I'm going to need to solve this. I'm going to cross multiply, so I'm going to get, well, actually, let me reduce this first. Divide both by 5. Alright, so I get that, and then I'll cross multiply. So I'll have 10 minus 6 cosines of theta equals 12 plus 15 sines of theta. Okay. I'm going to square both sides. Remember, we've done systems like this, we've done equations like this before. We square both sides so we can bring, we can use an identity for this one. And so that's going to give me then, for this side, that's going to be 100 minus 120 cosines of theta plus 36 cosine squareds of theta. 144 plus 300, let me make sure I do this right, 360 sines of theta plus 225 sine squareds of theta. Right? So we have a pretty big answer for ourselves. Right? Oh, you know what? I should have made this easier. I should have combined those like terms before I did that. All right, that would have made that a lot easier. Let me just go back and redo that one. All right, because that would make this a whole lot easier. All right, before I square, let me combine some like terms. So maybe I'll move the 10 over, so I'll have negative 6 cosine theta. Sorry about that, guys. Well, but look at how much better this is going to be, right? In terms of like squaring everything out and whatnot. All right, I square that, then I get 36 cosine squareds, and then 4 plus 60 sine thetas plus 225 sine squareds of theta. Okay, much better, because then I can just replace this with a 1 minus sine squared. And now I'm good to go in terms of having all one trig function there. That was this one. I wasn't that close, so I was way off. I'm sorry about that. Okay, so I move things around. Okay, just combining some like terms, distributing all my basic algebra stuff. So I'll move that over. So I have 261 sine squareds of theta. When I move that, combine those two, this one's going to be left to 60 sine thetas, and then I'll subtract 32 when I get to that. Okay. At this point, it'd be great if I could reduce it. I don't think there's going to be anything to reduce it because this only has factors that are 2, and that one's not odd. So we're going to go to quad formula it, right? So a quad formula says sine theta equals negative 60 plus or minus the square root of b squared minus 4a c all over 2a. Okay, and we put that into our calculator and we get a whole bunch of answers for ourselves. So the answers we'd get, okay, for it, remember that's going to give us the sine theta, and then we have to do the inverse sine theta, and we'll get a whole bunch. We'll get 0.2564 or 2.885, and then we'll also have negative 5.046 and 3.682. And not just put this in your calculator, get the two answers, and then think about what the sine answer is going to be. You're going to have your positive and your negative cases for it. So it's going to be, and I put everything in radians form here. Okay, so now we look at that and we say, oh my gosh, there's 4 answers. But remember, it's important to consider the graph here. All right, so if I look back at my graph up here, remember from the first one it was an ellipse, and so it was, I'm sorry, the first one was a hyperbola, right? And we found that the hyperbola had a focus here, and it was going to open like this. All right, for that first one, if I had considered what I'm going to consider it pi over 2 and 3 pi over 2 because it's opening up and down. All right, so the reason I'm doing this, I have 4 potential answers. Let me make sure there's really 4. There's 4 points where these intersect each other, so I don't have to go back and like test everything. Okay, so if I plug this in, right, pi over 2 for this guy gives me a radius of 10 over 9, 10 ninths, so that's that one right there. If I plug this in, that's going to give me a radius of 10 on top still, but negative 1, so radius of negative 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so my two are going to be kind of like that. Okay, no need to be perfect in terms of like getting every single bit down like the director sees and the foci, blah blah blah. We don't need all that. Okay, The other one, since it's opening side to side, I'll do the theta of 0 and pi. Okay. I could do pi over 2 and 3 pi over 2 if I wanted to. I just don't have to. These ones, that's going to help me get, these are going to give me the vertices because it's opening left to right. Okay. If I plug in 0, I get a radius of 15 over 2. If I plug in pi, I get a radius of 15 over, let's see, 8. Okay, so 0, right? Let me make sure I did that right. Okay, 0 has a radius of 15 over 2. 1, 2, 3, 4, 5, 6, 7 and a half. And then this is 15 over 8. Right? This is interesting that we always assume that the first one's going to be, over here, but in that case it's not. So you just deal with it. It is what it is. Okay, so our graph's going to look something like this. Okay, all right, for our cell, something like this. Okay, and if I look at that, I can see that I'm only intersecting one branch of it. It's hard to tell if it's above it or not, right? But I can see that there's really only going to be 2 intersections for this, not 4 as we did right there. Okay, if I think about where these angles are going to be, that would help me to say where this is going to be. Okay, the other thing I'm going to do is I'm going to figure out how high this one is, right? Just to kind of get a better idea. So if I plug in pi over 2 here, right, that's going to give me which one was the ellipse? Okay, right, this was the ellipse, right? Okay, yep. If I plug in pi over 2, just to see, so if I have my angle pi over 2, let's see, that's going to be 15 over 5. That's going to be a radius of 3, so it's going to be way up here. I was way too low. Okay, okay, it's going to be like way up here. Okay, so if I look at that, I can see that this is not going to intersect in the first quadrant. So any angle that's in the first quadrant's got to go. That's an angle in the first quadrant. That's between 0 and pi over 2. Gone. Right? No intersections in the first quadrant. See ya. Right? I can see there's going to be an intersection down here in the fourth quadrant. Where's an angle in the fourth quadrant? This is an angle in the fourth quadrant. So I'll keep that one. Okay? Right? Now I have to figure out, okay, is this intersection up here in the second or is it in the third quadrant here? So what am I going to do? I'm going to just kind of figure out for this, if I plug into the first one an angle of pi, just to see what happens. Right? So I'm going to have a radius of 10 over 4. Right? So, right, because that's going to be 0. Yep, okay. 10 over 4 is going to be 2 and change. It's going to be out here. So that means that this is going to come out here. So really, this is when you're going to use those other quadrantals to help you see where those intersections are. I can see my other intersections in the second quadrant. Second quadrant is a radian value between pi over 2, or 1.57, and 3.14. Right? So that means this is the other option. Whoops. Okay. Okay. So this one goes right here. Okay. So these are eliminated because of my graphs. Right? So these are the only 2 angles. Right? So now I take those angles, I plug them into either of these equations that I have, this equation or this equation, and that will give me the radius at those given points. Okay, right? So if I use this one, right? If I plug this into here, I'll get the radius is 1.898, and then 2.885 radians. Right? That's my one intersection. Okay. If I use this guy, and yes, I have it negative. It's okay, negative. You could add 2 pi to it. Right? If you add 2 pi, then great, good for you. It doesn't matter. But my angle is, there's nothing that told me how to be between 0 and 2 pi, so I use that negative one, and I plug it into either equation, and I get the radius then is 6.319. Okay? So those are my 2 intersections there. Pretty complicated problem. Yes, it is. All right, so do your best on those, and feel free to stop into the office hours if you need help on any of them.